Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be talking about the differences between ionic, covalent, and metallic bonding. So let's get into this. So the first one we're going to deal with is ionic bonding. So the thing to remember for ionic bonding is that it is a complete transfer of electrons, and this requires a metal and a non-metal. So the reason you need a metal and a non-metal is because the metals typically want to get rid of their electrons, and the reason for that is because they want that outer shell. So it's easy to remove electrons from the metal, and that would then give them their outer shell, and they would be like a noble gas having that stability. And so the non-metals love to take those electrons. So that would give them also an outer shell, a complete outer shell with an octet, and that would also give them stability. So when you put them together, a metal wants to give away an electron, a non-metal wants to take it. Without those two together, the element is just not going to give away the electrons. There's got to be something that's going to take them and something's going to give them. So putting them together creates that transfer of electrons, and that is what causes or creates the ionic bond. So the example I have here is sodium. Sodium has one valence electron in its outer valence shell here. And so it would love to get rid of this electron and then have that outer shell complete, the second energy level here. Chlorine has 7 valence electrons. It would love to have that one more electron to complete that outer shell. And so it would love to grab that electron from sodium. So bring them together. Sodium is happy to give the electron to chlorine. Chlorine is happy to take that electron, put them together, and that's what happens. So then you have sodium. Sodium has now an outer shell that makes it stable, so that's good. It's like a noble gas. And chlorine also has an outer shell that's full, and that's like a noble gas. So they've reached that noble gas configuration, but in the process, sodium loses a negative electron, and the electrons are balancing the charge of the protons in the nucleus. So you take an electron away, that's going to now have an unbalance of charge. You have more protons. You have one more proton than electrons. That gives it a positive one charge. Same thing with chlorine. Chlorine now gains a negative electron, so now it has one more electron than protons, and that gives it its negative charge. And so here then the positive ion is called a cation, and then remember that the anion is what we call the negative ion. So the chlorine is an anion, the sodium is a cation. And so what's holding these two together is the electrostatic forces that are coming from the fact that these are negative and positively charged. And we know that opposites attract, so it's that attractive force, it's that electrostatic attractive force between these two that's holding them together. And that, ladies and gentlemen, is the ionic bond. So what about covalent bonds? Covalent bonds is where you have a sharing of electrons, and in order to have a sharing of electrons, that's going to require a non-metal and a non-metal together. So no metals. So because there's no metal, that means that you don't have an atom that wants to give away electrons. Here, if you've got two non-metals, both of the non-metals want to take an electron. So they're going to want to have the electron. So it's going to be hard to transfer because neither non-metal wants to give away an electron. So what do? They're going to have to share. So just like children playing in the sandbox and they want to have the play with the same toy, they're going to have to share the toy. So here we have hydrogen and chlorine again. So here hydrogen is a non-metal. So hydrogen would love to have an electron that's going to fill in that outer shell and then make it stable like the noble gas helium. And chlorine would love to have another electron that would then give it its outer shell, a full outer shell, which would then give it stability like its noble gas, like the noble gas configuration. So then what do they have to do? So instead of transferring, they're going to have to share the electrons. So it would be nice to have an electron, say from chlorine, maybe this electron here, one of the valence electrons, to be shared with hydrogen, and then hydrogen's electron can be shared also with chlorine. So that's what we have here. So in this particular diagram or picture, I'm showing is a Lewis dot diagram. So all I'm showing here is the valence electrons. So the inner core electrons are being ignored here. And so you'll see here that when hydrogen is sharing one of its electrons with chlorine and chlorine is sharing one of its electrons, then there are two electrons being shared between the two atoms. So what happens is that that sharing of the two electrons gives chlorine a full octet, and so now it's happy. It has kind of a negative. It has an electron configuration of a noble gas. And so here, hydrogen also, with its two electrons being shared, now has a full shell, and now it is like a noble gas as well. So what's going on here is that you do kind of have an electrostatic interaction here, but it's a different from the ions because here, what's holding this together are the shared electrons. So the shared electrons are negative, right? And the protons of each atom are positive. So the positive nuclei are both attracted to the electrons being shared. And so the electrons kind of act as a glue holding it together. So you do have those kind of electrostatic forces, but it's due to the fact that the positive nuclei of both atoms are attracted to the shared electrons for the negative electrons being shared between the atoms. So that creates your covalent bond. And finally, let's talk about your metallic bonding. So metallic bonding is a whole new beast altogether. So here you have the positive nuclei of the atoms. So here I have in red the positive nuclei. And of course, you have the negative, you have the electrons surrounding the nuclei. But you'll notice that the electrons in blue here are dots, and these electrons are delocalized from the atom. So we're looking in particular to the valence electrons, and so those valence electrons are no longer held to the atom itself. They can be shared amongst all of the atoms in the metal. So what happens here is that the electrons kind of create what is called a sea of electrons. So think of islands in an ocean, right? They're surrounded by the water. So the water is held in common with the islands. So the water can flow among the islands, or you can think of submarines in the ocean surrounded by water. So the water flows around each of the submarines. And so that's analogous to what's going on with the electrons. So the electrons here no longer belong only to one atom, but they belong to the whole substance, and they can they are what is called delocalized. And what that means is the electrons are kind of detached from any particular atom, and that allows them to flow. So if I put a force on them, like for example, if I hook up electrodes from a battery to a metal, I can get the electrons to flow through the battery or light up a light bulb or something like that. So the flow of electrons can easily occur through the different atoms, and the reason why that's possible is because the electrons are no longer localized to one particular metal atom, but it is delocalized and allowed to flow and become the electron of a different atom. So there's a flow here allowed. So that's what you see here. And so this is also what gives metals its malleability and its property, because the negative electrons are all kind of attracted to the positive nuclei of the atoms making up the metal. And so you can move and jostle these atoms or nuclei around, and so it'll still stick together. So you can think of the electrons being the kind of the glue that's holding all of these atoms together, and that's what creates a metallic bond. So I hope this was helpful. I hope this kind of clarified the differences between ionic, covalent, and metallic bonding. If you like this video, please hit that like button, subscribe to my channel, hit that notification bell so you can be notified of other videos I put out. Put a comment in the comment section. Let me know what you think. And if you have any questions, I can answer. Thanks for joining me. Have a great day.